It's time to study an important equation in math, an important concept in mathematics, an important concept in mathematics, an important concept in math, and we're going to study it. We're going to study this important concept in mathematics, in mathematics. What is this important concept? Could it possibly be the thing that has been sitting here on the title slide while I noodle? Yes, there's a strong possibility that that is in fact the topic of the day. It is the Fourier Transform. This is going to be the extension of the Fourier series into the next step of awesomeness. It is going to be I can't even say this with a straight face. It's I'm so sorry. It's one small step in concept and one giant leap for your calculational abilities. So what we're going to do is to take the discrete Fourier series, this idea of taking a function, looking at its frequency content, and building it from a sum of sine and cosine components. Now we are going to take that discrete process and build it up to a continuous process. So of course, spoiler for everyone who's taken calculus, our sums are going to turn into integrals. Yes, even more integrals, but it's great to integrate. That's why it's called integrate, because it's great. I don't think that's why it's called that. Okay, this is going to be certainly a bit more challenging in executing the calculations. The idea isn't that much crazier conceptually, but when you start thinking about everything in continuum, it just really it gives you new ways to solve problems. Some of those we'll get to this semester, some we won't, but I want to at least highlight over the next couple of videos what the ideas are, what the concepts are, what the utility is. In this video, I'm actually just going to start with a calculation. I just want to show you the process of how do you do one of these, because we don't typically do as much of that in the videos, and the math gets hard enough that it's really nice to have examples to follow as you try to do your own, and I'll revisit that point later. So let's do some math. Again, the unpacking of the concepts will come over the next few videos. So if we have a function f of x, little f of x, there are two requirements here. It needs to be piecewise continuous. So it doesn't necessarily have to be smooth, but it does have to be continuous. So no jumps, no gaps in the function. And it needs to be integrable. Now, that doesn't necessarily mean that the function has an antiderivative. I've made this point before, I want to make it again. An integral and an antiderivative are not exactly the same thing. You can integrate a function without knowing how to anti-differentiate it. Spoiler, we're going to see that real soon. What I mean by integrable is that when you do the Riemann sum, it converges to a value that our function can't have lots of big infinities in it, because then you can't do sums and add those together. You can't have any like divide by zeros or weird stuff unless they're particularly large values for zero. And before I go further down that rabbit hole, we should move on. The way that you write the calculation for doing this, for finding the Fourier transform, so again, this is basically the continuum version of a Fourier series, is given by this integral. And this does look pretty similar to the complex Fourier series that I introduced in the previous video. And the whole reason I introduced the complex series was really just to be able to get to the transforms. So you can see that we had this e to the I kx going on, and that is the same term as the e to the I cnx that you saw in the complex Fourier series previously. We are going to be integrating over all real values of x. So we are going to sample the entire space that our function contains. And what's going to come out is we're converting from a function of x, a function of space, to a function of some other variable. What is that other variable? Well, I'll answer that question soon. But once you find it, you can invert this transformation. You can run it backward. And the way that you run it backward is to do this reverse transform. So this will be the operation that takes you from k space into regular old coordinate space, forward, backward, left, right, all that. So what is k? I've just thrown in this variable here like, hey, here's a variable, but it has to have some meaning. Well, the meaning is the frequencies that are used to build up our function. So we had our initial function of x. Maybe it does not have to be a periodic function. It can just be any old, like, I'm a function. All right, so here's f of x. Then the Fourier transform of this function is going to tell us, and I do not have this example prepared. I have no idea what the Fourier transform is of this thing that I drew, but whatever it contains, if the function is high at certain points, like maybe it's high right here, then that would indicate that that function has a large amount of frequency content at this particular value of frequency. And if the transform is low over here, then it tells you the original function does not have a lot of content from this higher frequency. So these are the sorts of relationships that you can inspect in these functions and their transforms. But how do we calculate them? Well, actually, first, I should say a little bit more about this k business, because I've just been calling it the frequency. But what I mean by that, to be more specific, is that the variable k here, units-wise, if we do our dimensional analysis, x is position, this is meters. The argument of e to the whatever has to be unitless. And because this is an oscillating function, that unitlessness is really units of radians. Meters per meter. I mean, that's the units of radians, really. It's a circumference over a diameter. It's meters per meter. Then this is the per meter in that ratio is k. So the meaning of this, the reason why it's a frequency, is that it is your number of, this really is the way I think of it, it's your wiggles per meter number, or as I've written here on the slide, radians of oscillation per unit distance. It's wiggles per meter. So if k is a large number, that means we have many oscillations within a given space. That's a high frequency. It's a spatial frequency, wiggles per unit of distance, or radians per unit of distance, being actually correct about it. So this is why I'm calling k the frequency. Now, all of this video, I'm just going to look at position x and then wave number k. In the next video, we will look at time. So things like signals, things that change over time. But for now, space. Okay. The reason I'm going to do math and really focus the rest of this video on the math is twofold. The first reason is that, as I said earlier, having example calculations that you can use as guides to figure out how to do this stuff is really helpful. It's super not obvious how to execute some of these integrals, and it's one of those topics where you build up a bag of tricks over time. So studying other people's tricks and benefiting from them is really fantastic. I recommend it as a study strategy. But the other reason is that the calculation that I'm going to do is going to answer a really very, very fundamental question in quantum mechanics. And as I've made a point of saying in this class, quantum mechanics is the language of atoms. Materials are made out of atoms. This is very much a material science topic. It's not just a physics toy. All right, so what's this important problem in quantum mechanics? Well, let me remind you that we have this proportionality between momentum and wave number, as seen in the Schrodinger video. Okay, great. Here is our problem. Here's our example that we're going to walk through. I'm going to give you a spatial function and ask, what is its Fourier transform? Here's our function. It is a Gaussian. So it's centered at x equals 0. I did actually put my axes in the right place, and something like this. So here's our function f of x. And remember that this width of the function is related to the parameter a. Now, for those of you who have taken a statistics class, if you remember your business about normal distributions and standard deviations and all that, there is absolutely that connection here. So if you've seen the normal distribution written as like e to the negative x squared over, I hope I'm remembering this correctly, 2 sigma, then that sigma is the standard deviation. That's the width of your Gaussian. So this width of the function is essentially 1 over a. And yeah, there's a factor of 2 or something in there depending on how you define things. But the point is, a is our parameter that tells us, is this a narrow Gaussian or a wide Gaussian? So now we throw this function into the formula. There's going to be a lot of equations on the next few slides. Feel free to pause, read through things, take your time, study step by step. Okay, so the first thing to do is we've put in our function. Here's f of x. And because these two terms in the integrand are both exponentials, we can combine the arguments of the exponentials and make it a single exponential function. This is already a good thing because exponentials are functions that we know how to integrate. Kind of. The kind of here is that there's that really tricky little x squared to deal with up there, but we will deal with it. Okay, this is where the fact that in a previous life I taught high school math comes to really save the day. Because the thing I never understood and never valued as a student was completing the square. When I was in, I don't remember, 10th grade or whatever, and we're doing completing the square to do quadratic equations, I'm like, this is the stupidest thing in the world. Why wouldn't I ever just plug things into the quadratic formula and be done? And the answer is really, if you're solving a quadratic equation, completing the square is rarely, I'm not going to say never, but very rarely the fastest way to do that. But that concept of recognizing how to manipulate an expression to express it as a perfect square, because then you can work with squared quantities, like to cancel out a square root operation, for example. That is actually a really handy tool to have in the toolkit. So we're going to complete the square. Here I have combined the exponentials as in the previous slide, and then I've just factored out this a coefficient from both terms so that we have something a little bit simpler in the middle here. Now, I know it looks like it got worse. Okay, technically it did get worse, but it's going to get better. Look at the signs carefully here. And yes, I've left my I squareds as I squareds on purpose. As I just hinted, we want to think about square quantities here. So I have written I squared instead of -1. That's on purpose. But I have plus something and minus that same thing. I have not changed the value of the expression. I've added and subtracted equal things, so my net change is 0. But it's written differently, and that can help you recognize patterns in the expression to manipulate it without actually changing the value of the thing. And when we do this, then two things happen. First, this term on the right, I have now written my I squared as -1. So I'm going to have negative, negative, and that turns into the plus k squared over 4a squared on the right here. And then the left term, these three things, x squared plus ikx over a plus I squared k squared over 4a squared, that is a perfect square. That is the square of, as is written down here, x plus ik over 2a, quantity squared. If you FOIL that thing, multiply it by itself, you'll be like, oh yeah, that sure does work. That's those things multiplied. This is why we complete the square. It actually lets you simplify expressions even when you're not solving for zeros. All right, cool, great. Our factored out a is still hanging out front, and now we have the sum of two squared quantities inside that exponential. This is progress, I swear. We're going somewhere with this. So now we have to do just some turn the crank arithmetic, some manipulating here. This is the same expression as the last line, I just copied it. Now, if you look at how this thing is written, you have to pay attention to what variable is your variable of integration. We're integrating over x. We're trying to solve for k, or solve for a function of k, and we're doing it by sampling the function f of x at every single value of x. Remember, that's the bounds of our integral here. X from -infinity to x equals +infinity. So we're scanning over all of space in order to find and collect the frequency components of our function. Because this is an exponential and because x is a variable, this entire thing on the right, that is just a constant term. C is a constant, looks at me. K is a constant, A is a constant, 4 is definitely a constant. So this is e to the some stuff times e to the negative distributive property here, a times k squared over 4a squared, and that whole thing is a constant that you can pull out front. So that's what's happening outside the integral now, is we've taken the constant part of the exponential and factored it out from the integrand. What is left in the integrand is the function of x, which is our variable of integration. So looking at this, you're like, I don't actually know if this is better. It almost looks worse because I still have an exponential inside, but now I have stuff outside also. It's okay. We're getting there. This problem takes a few steps. These Fourier transforms do just take a while, even one that's, I hate to say this, but relatively simple like this one. There's just a lot of arithmetic to work through. It's it's a good workout for your math muscles. Anyway, what I've done in this next line is just to pull the a coefficient inside the squared term. That's just going to give us a little bit less stuff to keep track of as we go through the integration. So we have now pulled out the constant part of the exponential, and we've factored all the other terms into this single squared quantity, so it's just e to the negative something squared. And that is a good thing because we do a u substitution. We're going to redefine our variable of integration, and we're going to go from x to u. I mean, that's why it's called a u substitution, of course. So this entire business, e to the negative stuff squared, that stuff is going to be our u function. And this is great because when you take a derivative of it, then the ik over 2 root a, that's a constant term with respect to x. And that means that du is just root a times dx. It's just the coefficient of the linear x term, and that's it. And d of the other stuff is 0. That means that, and this is why I wrote it as square root of a x inside, this is just e to the negative u squared. And there's a constant of proportionality here. That's fine. That's a constant, so we can pull that out of the integral as well. And then it's really just e to the negative u squared du. So at the end of this, our integral has actually gotten way simpler than what we started with, because everything else we were able to rearrange into combinations of constant terms and pull those constants outside the integral. Now, for the sneaky part. This actually came up in class just yesterday. I mean, class yesterday. Last time I was in class, anyway. It's dealing with this integral, this essentially e to the negative x squared integral here, because this is what I was hinting at the beginning of the video. This function does not have an analytic antiderivative. There's no simple function that you can write down whose derivative is e to the negative x squared. But that doesn't mean you can't evaluate this integral. You can evaluate this integral. The way you do it is, unfortunately, I'm already starting to run over time here, so I'm going to have to skip it. But it's a very clever trick. You learn it in Math 215. Feel free to ask me about it in class. The value of this integral is square root of pi. Ta-da! So I'm skipping the algebra there because I want to get to why it matters so we can wrap this thing up. At the end of it all, the square roots of pi cancel out, and we just have actually a very nice simple expression for f of k. So this is saying that the Fourier transform of our original Gaussian function is a Gaussian function, but it's a little bit different. There's a really important difference. So here was our initial f of x. Here's our new big F of k. These are pairs. These are like partner functions. One of them is a spatial function, one of them is a frequency function, and they go together. They're like peanut butter and jelly. And you're like, but they're the same damn thing. No, they're not. Because the space function is x times a, the frequency function is k over a. That is very significant. Okay. So what this tells us physically is that when you have a wave pulse that looks like that, then its frequency content looks kind of like that. Okay, I missed. Its frequency content looks kind of like that. And the difference, or not the difference, but rather the interpretation of this is that most of the frequencies that you need to build a Gaussian are within this central range. And then you need a little bit of these further away frequencies, a little bit of high frequency, a little bit of low frequency, and lots of medium frequency. That's how you build up a Gaussian wave. If you find that exciting, great. If you find that boring, let me convince you why it matters. So, why it matters. This was the punchline. This was the whole conclusion I wanted to get to. We talked about Schrodinger's equation. We talked about wave functions. And so if I have, we'll say, pick my favorite diffraction thing, neutron. No, actually, let's have an X-ray photon. Yeah, that'll be fun. So like, imagine we're doing a diffraction experiment and we want to talk about the photons, the X-ray photons that we're sending in to do X-ray diffraction. Well, these are localized entities. And if our wave function for our little photon packet looks like this, then that tells us the frequency content of that bundle of photon. But the relationship I want to highlight is this. If we had a very narrow, I missed. If we had a very narrow spatial distribution, originally, like that, then that would have been a narrow spatial wave packet. That would correspond to a really wide range of frequencies. On the other hand, if we had had a really spread out wave distribution for our incoming signal, that would mean that its transform is very narrow, that it has a much tighter spread of frequencies inside of it as a result of that initial wave being much longer and more spread out, delocalized, if you will. Here's why this is a big deal. This says that if you try to take a wave, any wave, this is not just a quantum mechanics thing. If you take any wave and you compress that wave, like this guy here, you try to make a really narrow wave packet, you squish that wave into a small space, the inescapable consequence, the mathematical requirement for the frequency components of that narrow wave pulse is to have a wide range of frequency components in it. There's no other way. It's inescapable. This is like fundamental nature of reality stuff. On the other hand, if you want to have a signal with a very narrow range of frequencies, so think of like a laser beam, right? A monochromatic source that just has one single frequency in it, then that wave has to be very spread out in space. It has to have this very wide envelope in order to make it mathematically possible to have just a couple of frequencies inside that wave. And the reason this is important quantum mechanically is because it means that there is a trade-off between these two functions. Remember I said A was essentially the width of this function. So if I have my wave function that has some uncertainty in x, then that tells me that there is going to be some corresponding uncertainty in its frequency content, delta k, and I've called this the k-axis, but all you have to do, since after all, momentum is just h bar times k, we can just multiply this axis by h bar, rescale the units, and then bam, suddenly this is our momentum distribution. And there's an inescapable trade-off between these two things. If I multiply my uncertainty in position and my uncertainty in momentum, if one of them gets smaller, the other gets bigger. It is impossible to build a localized wave function out of a small number of frequency components, which is really momentum components. In order to make a function that is squeezed into a small space, it must have a large range of momentum values. And there is a minimum that you can possibly achieve with this multiplication. And this is where those coefficients, the 1 over square root of 2a, in these Fourier transforms, this is actually how you calculate this value. This is where it all comes from. So this is great stuff, but this is the fundamental reason why we have the uncertainty principle in quantum mechanics. It's not about something spooky that electrons do that's special. It is a property of all waves. Anything that is built out of waves has an uncertainty principle. And because the world is fundamentally wavy, that's the key thing about quantum mechanics. Everything has wave aspects. That means everything has an uncertainty principle because everything is a wave, and all waves have this trade-off between constrained positions and constrained frequencies. You can't limit both of them indefinitely. One shrinks, the other grows. So that's why this matters. I have a couple very quick notes before I wrap this up. I want to point out that when you're trying to do problems with this, you can take advantage of the fact that this is a linear transformation. That means that if I have the sum of two functions, then, oh dear, spoiler for next time. Next time we're talking about time, but you could just imagine x, k, k here. but the Fourier transform of the sum of two things is the sum of their individual transforms. So if you have a more complicated problem, but you can break it up into a sum of smaller problems, then you can do those individual problems and add together your answers at the end. So that's really nice. As far as how we'll see this in this class, because people are always like, so how will we use this? Well, we're almost at the end of the semester. There will be a couple of homework problems where we look at some Fourier transforms. We will be implementing this numerically as well, so you'll see how we do this with a computer. But on the quizzes, I'm not going to have you do any of these calculations. Like, it just took me 30 minutes to get through one, basically. Now, okay, we'll just leave it at that. Like, this would be a lot to put on a quiz. But I absolutely do intend to ask at least one conceptual question about, hey, what is the meaning of this stuff? So think about drawings, think about examples, think about applications. Like, that's the kind of content I'll ask about quiz-wise. We'll have a small number of calculations on the homework, but as you're doing problems on this, I really encourage you to look these things up. This is getting to the point in the math where stuff is just hard. And I'm not saying you shouldn't try. You absolutely should try. You build up your brain by exercising it. But if you're spending hours, like literal hours on a problem, don't do that. Stop and be like, maybe I should get some help. And looking up how other people have done things is absolutely a valuable strategy. There's some really good research studies on how people learn from studying solutions to problems. It's a very effective practice when you do it thoughtfully and don't just copy the answer. So this is my advice on all of this is, yeah, feel free to look things up, feel free to study other people's solutions. If you want to talk to your favorite language model about getting tips and getting unstuck for that, that is also a very valid resource. At the end of the day, just make sure that you're not straight up copying what's out there and then calling it done and be like, I got the answer. The answer is not the point. The process is the point, right? I want you to learn at getting good at this stuff, not produce solutions. I'm not assigning any problems where the solution is important. We're not inventing new knowledge here. It's just a class. So, um, as you're looking up solutions, as you're talking with chatbots, classmates, whatever it's doing, whatever you're doing, again, just make sure you're putting in that level of mental engagement where you're saying, why is the solution this way? What is this part that I don't understand? Can you explain that step? What's going on here? Just make sure you're in the game. Okay. I know that video was forever long, probably the longest one of the semester, but the next one will be quite a bit shorter, and then that'll be it for today. The next day, the next set of videos, we'll look at implementing this computationally. All right, see you soon.